All right, we are getting into nonlinear relations today. We're going to continue on the path we were discussing before. This is called the general linear model, so you might be saying, wait, it's the general linear model. We've been talking about linear relations this whole time. I just keep talking about linear equations. What the heck is a nonlinear equation? Well, it's actually a family. But first, the linear equations that we've been using, the GLM, the general linear model, or regression models, they are additive models, or they're models that have interactions in them. But essentially, the prediction models that you're creating, these prediction lines that you're making, they all result in a straight line. One straight line that connects the predictor with your outcome variable. So you get conditional mean of each y value of x, and every time that you solve an equation, like when you solve for y, using that equation, all those results you plot in a straight line. That's all. So 1 unit increase in x is always the same increase in y. Here's a linear relationship. A 1 unit change in x is always equal to the same amount of change in y. We've drawn a lot of lines in this class. Here's one. Now this right here is a nonlinear relation. This is an exponential change relation. So this predicted line is not straight. When I solve the equation for y, depending on what I plug in for x, I'm going to get a not straight line, but a curved line representing the relation between x and y. In other words, the rate of change, how big the slope is different from 0 to 1, and it's different from 1 to 2, and different from 2 to 3, and so on. Each one of these slopes is slightly different. Here's another example of a nonlinear relation. Here, the slopes are still different between when I've solved this equation. When I've solved it, when I've plugged in 0 for x versus 1 for x, that's a bigger difference than 1 to 2, which is a bigger difference than 2 to 3. Why would I be interested in nonlinear relations? Well, maybe with pandemics, we might have more of a reason to think about nonlinear functions. You've thought about nonlinear functions for quite a while, exponential change as things spread more quickly, and maybe decelerating change as things slow down. Now that's just about means, though. That's not really about relations. So here's an example. Maybe to put this back in the context of my break activities, I'll say the number of ounces of wine consumed and how productive I am when I'm writing. That doesn't work for 12 ounces. For the first 12 ounces of beer that I drink, my productivity tends to skyrocket, go way up. I write much faster. I just get a lot more words on the page. But after that, that relationship slows down. And if I have 4 beers, honestly, if I have 3 beers, then that relationship goes down. I can no longer write because I'm too distracted by other things going on, or I'm too sad, or I'm too incoherent and can't put thoughts together. That is a relation between amount of alcohol consumed and writing productivity in number of words written. It looks like that. Now, for an actual example that's not just silly, so there's a study from 1967, and he thought that he could get people to engage more in healthy behaviors through fear by making people feel afraid, but only to a point. So if I scare people a little bit, then maybe they'll shape up and do this thing I want them to do. But if I scare them too much, they'll get overwhelmed and not want to do it anymore. So again, that's a relation that looks kind of like this. Scare people a little bit, productivity goes up, or the behavior goes up. Scare people too much, it goes down. Or have you heard of the Yerkes-Dodson curve? If you haven't heard of the Yerkes-Dodson curve, you should look it up. It's excellent for graduate school. The whole idea of the Yerkes-Dodson curve is a relation between stress and productivity. And it's when you are not stressed at all, you are not productive at all. And as you get a little bit stressed, your productivity goes up. And it keeps going up to a point. And I'm sure you all know that point. Once you hit the point where stress is just too overwhelming, all you can do is have a no-bones day and lie in bed all day. You just have to not do anything, pull the covers up, and just hide. So that is a nonlinear relationship. Does that concept make sense? That, like, sometimes you expect a strong relationship and sometimes you expect a weak relationship. I got some nods in the room. How about at home? I got a couple of thumbs ups. All right. That's the concept. So if I actually think a relation like this exists within my data, how would I test for it? So we know that the general linear model, regression being one of those options, only fits straight lines because of the definition, a linear model. So what we have to do is we actually trick these equations into fitting nonlinear models using parabolas. Do you remember those from Algebra 2? I remember you had to go out, one of the assignments was go out in the world and find something that is a parabola, and then you have to try to graph it on your graphing calculator. I wonder if they still do that. Don't know? No, they don't? Create maybe a McDonald's arches or something? Anyway, parabolas. So what we're going to do is we're going to add in not just x, that's our original variable, but then we add in x squared. That's a new variable that we put into the model. And it looks like this, variable 1, variable 2, which is variable 1 squared. So it just fits right into your same linear equation you already know and love. This should be a y hat because I don't have an error term. So let's just take a look at this. The regression model or the GLM, ANOVA model, they all think that it's analyzing a linear relationship. They don't actually know. We're just tricking it with math. So here you can see how that transformation works. If I've squared variable 1, 8 becomes 64. That's all I'm showing you with these data. So what we're going to do is multiple linear regression and take a look at it. So what I've done here is I've taken some fake data on the relation between number of questions you get right on some sort of test and the amount of time you spend practicing. And I was thinking at the time of this of something like a memory test, like you have to memorize the numbers or the digits in pi. So if you only spend 2 minutes practicing, you're going to get 3.1415. Oh, 3.14159. But then if you spend 4 minutes practicing, you're going to get, I don't actually know the next two, 3.1415916? Do you know? 2? Whatever the next two are. And so on. You can tell these data are fake because look at how close together I've made these people. These are clearly fake data, but it illustrates the point. So the research question that I might have here is, does spending more time practicing result in better test scores, or does that relation change with more time spent practicing? So once I've put this into, here I have done it in a regression model. Remember, what we do is we put in both the original linear term and then we put in the square of itself, the quadratic term. So I get a constant, just as I did before. I get a coefficient associated with the linear term and a coefficient associated with the quadratic term, the squared term. So this here tells me that the linear term is significant, and this here tells me that the quadratic term is significant. So let's talk about interpretation. So just for a second, think about what I've just done is I've taken one variable and I multiplied it times itself. Now, do y'all remember in interactions, what we did is we took one variable and we multiplied it by another variable. And then we had to interpret things slightly differently once we used that multiplication term. Here I've really done just exactly the same thing. I've multiplied one variable times itself. Which means my interpretations are going to be very similar to how they were when we were interpreting an interaction model. So, let's do that. Remember, with interaction models, we're always really concerned with where on each variable we're located in regards to 0. Which means that my intercept is going to be when you spend 0 minutes practicing, you're going to get negative 1.9 questions right. That doesn't make a lot of sense, but we remember what we talked about with our linear equations, and our nonlinear equations have the same problem, which is they go on to infinity. We didn't have anyone who spent 0 minutes practicing in this data, so that's not a great representation of reality. So now we have variable 1, which was the linear effect. That's also sometimes called the main effect we talked about when we were looking at the interaction models. So here we say, when variable 1 is 0, with 0 minutes spent studying, an additional minute of time practicing, we would expect to see 3.5 more questions correct. Remember how that slope changes every time when we looked at that equation, that linear model, nonlinear model graph? It went up, and then it was less steep, and then less steep, and then less steep. So here, the interaction variable, variable 2, says, there is a significant nonlinear effect of time on studying, such that the relation decreases in strength as time increases. That's what this decreases in strength. So from these pieces of information, I know that we're going to you can kind of see that. I know if this is 0, my y-intercept is going to be negative 1.9 down here. I know it's going to go up. So this is 0 minutes, this is 1 minute, 2 minutes, 3 minutes. I know it's going to go up by 3.5 points the first time. 1, 2, 2, 4, 6. I know it's going to go up by 3 points the first time, 3.5 points. It's 2 plus 1 more is 3. The first time it's going to go up by 3.5-ish points. The next time it's going to go up by 3.5, but take back again 0.138. So instead of going all the way to 3.5, 1, 2, 3.5, it's going to be a little bit less than that. So that slope is slightly less steep. And so on. Which means if I've practiced for, this is why it's so important to keep your data within your observed range, keep your interpretations within your observed range of data. But if I study for 100 minutes, okay, if I study for 1,000 minutes, this variable 2 here, this interaction term, suggests that eventually I'm going to get worse the longer I study. Because parabolas have that unique, they all look, if you look at them all the way zoomed out, they all look like this. They all have that effect. How fat they are or how skinny they are depends on the parameters that you're looking at. So anytime we're fitting an equation like this, we're just grabbing one chunk of that place on that model. Mm-hmm.
How do you know what chunk you can trust up to? Just like your identifiable data, that's it?
Just your identifiable data, that's it.
Okay.
Same goes for all of the linear equations. It's just a little less extreme with the linear equations than it is for the nonlinear equations. So once again, remember the goal of all of this, we're doing model comparisons. So the whole goal is to reduce the error in the model. So if a curved line fits better than a straight line, then the curve part of it is going to do a better job of decreasing the error, and we'll see a statistically significant relation. So I'm just showing you here that if you had run this without the quadratic term in the model, then we would just say we expect it to increase by about 1.5 questions for every minute spent studying. But then once you add in this term, you get a very different understanding of what's happening. Oh, look, I give you all of those interpretations. Now, the other thing I give you here is the equation. Now you're pretty used to pulling things out of this equation and putting them into, or out of these sort of tables and putting them into equations, I think. So you know where the B0 would go, the B1, and the B2. So then here, if X is 5 minutes, if I want to know about 5 minutes spent studying, I would plug in 5 right here, and I would plug in 5 squared right here, 25. And that would give me my expected Y for 5 minutes of studying. Let's take a look at what it looks like. So right here, what I've done is provided you with the graph that I started to draw behind me. You could, oh my gosh. You can see that this relation is getting weaker the higher up it goes. So this coefficient here really is asking how fast is that curve changing as X is increasing. So variable 1, just to like get a little bit mathy on you here, variable 1, which is the the main effect. The main effect is the tangent of this curve. See how it just touches this line at one point. So this 3.5 is the tangent of this part. Now if you keep going up, there's the tangent to this curve. This is a much weaker slope. And so like I said, we're just sort of moving the window of where we're looking within a curve that's shaped like this. Ooh, there's another one. Eventually, it's almost 0. So I pointed this out already, but remember, negative 1.9 is possible because this is an extrapolation to someone who spent 0 minutes studying. It's not actually observed, it's an extrapolation. It makes our line fit better. Even if we had 0 data, it's still possible that we would have gotten an off-the-chart result for this. It's the consequence of trying to fit lines to things. And reinforcing here the idea that this 3.5 is the simple slope when x equals 0. And simple slope means the line that's tangent to the line. So it doesn't tell us anything about the rest of the values of x, only about this particular value of x. Which is actually exactly the same as it was for interactions. With an interaction model, it's only telling us about the slope for this value of x2, not for any other value of x2, just this one. And this is, again, just reiterating here that B2 describes how the slope changes when x is changing. So it's becoming less positive. You might also say the curve is decelerating. But that relation between x and y is getting weaker as x gets bigger.
Can I ask about the applications of this?
Yes.
So if we're only getting information about that one particular point, then how are we use it to predict if that's a linear line in the end?
So if we're only getting information about one point, how are we using it to predict? Did I reiterate that correctly?
Yes.
So the whole point is that we're going to look at, let me back up to show you the picture. So if you look at this picture here, this first slope is just giving you the statistical significance of one part of this line. Not the whole line, but just one part of it. This relation right here is telling you whether that line is straight or not straight. And in both of these cases, we're looking at how much of the error variance we've reduced in our model by including these things. So just like with an interaction, you can never say, yes, this variable is definitely related. What you can say is that it's a nonlinear relation. It's related such that it's steep, but it gets weaker as the x value goes up. So in my example with drinking beer and being productive, writing productivity, I will reduce the error in my model by adding in the quadratic term. In which case I can say, on average, I write 20 words a minute, but the longer that I drink, the more alcohol that I drink, the less steep, the more alcohol that I drink, the relation between how much alcohol I've had and how productive I am goes down. So you're never talking about when you're talking about whether these variables are predictive, you talk about it as a whole. And when you're describing the relation, you describe it using these numbers to talk about the strength of the relation and how that changes across the distribution. Now I think I'm done answering your question, and if that, did I get you anywhere or not yet?
If we plot the
Wait. Say
the equation that comes out using that V2, you're saying that that's a straight line, right? A linear line, not a curve.
Sorry, I missed the mute button. This green line right here is the equation, is the line that you get if you plug in these numbers into the equation. if you use these numbers to make an equation and you plug in all of our observed values of x, this is the line that you get. It is a curved line.
All right, I was confused. I thought you meant that it was referring to the tangent line, not the curve, the whole curve at least.
Yes, so all of these things together, the negative 1.9, the 3.5, and the negative 138, together they make this whole green line. So let me give another example, and then we'll see if that helps clarify things. But make sure you speak up again, Sarah, if it's not clearing it up. Okay. So in this instance, we would say that the relation between the outcome and the predictor is nonlinear, that it shows some sort of deceleration as the value of x increases. So let me give an example where this has come up in the work that I've read before. So what I've done here is I've used the data on preschool children's math knowledge, and it's from a study of the Sesame Street TV show. It was an evaluation of the Sesame Street TV program. So I have a couple of variables here. The first thing I have is a math score, which is about like how you count, how much you can add numbers together, and then their knowledge of size comparisons, which one's bigger, which one's smaller. That's called like relative size. This is num for number. And then I have a gender variable, which in this study was male or female. Now, theoretically, I would expect that size comparison is a much easier skill for kids to get. And so that if you already know size comparisons, that it might predict your scores on math. Because the thing about size comparisons is that really, this is just vocabulary. Bigger and smaller, those are just vocabulary words. An understanding of math vocabulary words is one of our really good predictors of later on math knowledge, like ability to add things together and subtract things from each other. So I'm going to look at the extent to which knowing size words is related to number knowledge, and I'm going to control for the gender of the child. So I'm going to show you this SPSS code. It's the same code as we've had before, because first I'm going to fit the linear model, and then I'm going to add the nonlinear term to it. So here's our result. And you see here that we have a pretty good R-squared. Our R-squared is about 0.52. We have significantly decreased the error in our model, generally. The intercept has decreased the error in our model. The pre-test score has also reduced the error. This gender term has not decreased the error in our model, but it's in there because we wanted to control for potential gender differences. Here are our parameter estimates. We see that their intercept here, which is, see if I put the, I didn't, so I'm going to say it out loud. When gender is 0, and when the number of words they know is 0, our expected score on numbers is about -5. There's no significant difference between the boys and girls in this sample. It's about 1.5 points, but no significant difference. And our and our relative size, as that goes up, the number knowledge goes up as well. So this is confirming my hypothesis that these two things are related. So now if I want to next examine a nonlinear relation, it changes our research question somewhat. So now the research question is the relation between math concepts and size comparisons dependent on the child's score on size comparisons? Still controlling for gender. So why would I think this? It's because traits like this one often show floor or ceiling effects. The thing about studying child development is that we're studying things that are just starting to happen or that they're mastering. So it means sometimes we have pile-ups on either end. When we have a pile-up on either end, we tend to have weaker relations between things because there's nothing that individualizes or differentiates between them. So I might expect that there would be a stronger relation at the higher end of children's skill. That pretty much at the beginning, nobody knows how to do things. It doesn't really matter. But the kids who really knew how to do this before, they're really going to know how to do math later. So the conceptual question is that relationship dependent on just how good you were at this to begin with? So let's look. The GLM code is really nice because all you have to do to put it in the model twice, to put it in the model with its square, is to type that you're multiplying it together. So here, pre-relative size, relative size times relative size. Now I have this whole new thing in the model right here. And you can already see that I have reduced the error in the model by including this. I've gotten closer to all the points. Ooh, look, an arrow. Look, another arrow. So let's look at this nonlinear output. How do we read this? I have here an intercept, which is now very different than the intercept we had before. I have a gender term still in the model. Gender is still not associated with our outcome. Here's a good example, I think, Sarah, that plays into the question you were asking, which is here, the main effect at this point, negative 0.388, is not significantly different from 0. But this nonlinear term is significantly different from 0. So can I use these terms? I'm going to ignore gender for right now. Can you use these terms? Grab a piece of paper, grab an iPad, whatever you're using, and see if you can jot down a little axis. See if you can draw what you think this line is going to look like. And I'm going to give you 5 minutes to do that. Okay. Now, I think can you all at home see this, the Jamboard?
Yes.
Okay, thank you. So what I have here is, we have a couple of different responses to the prompt. Let me put this down here. Here's our equation that we're trying to graph. And so I think it ended up being really helpful for people to, instead of just think about it conceptually as like, what's a negative slope and a positive quadratic? What does that mean? To actually solve for y and then plug some things in. So we end up getting a function that looks something like this. And then we had one group who gave us all of the predicted scores here. And so what I like about this example is that it shows you that with 1, we're going down a little bit, and then as you go up, it starts to go back up again. So you can see 7.5, then 7.6, 7.9, 8.6, 9.6. So that strength of that relation is getting much stronger as your x value goes up. So if you're looking at something like this and going, okay, well, I've looked at my significance tests, and I know that this variable is related to my outcome, but what does that mean? then graphing it is always a great way to try to figure it out. Now, I heard a couple of questions in the room through my headphones that I wanted to try to address. It said something about, but is it significantly related? Is that,
Yeah, we're talking about the significance values. So like the intercept is significant and the quadratic term is significant, gender and free roulette are not. But then we were talking about free roulette, it doesn't really matter whether or not it's significant because that value is changing but only at 0. So that's what the discussion is.
yes, exactly. So in case you couldn't hear that, let me reiterate. She was saying that here, the intercept is significant and the quadratic term is significant, but this one's not significant. And how do we interpret that when it's not significant? But it doesn't really matter that it's not significant because it's just at one point. And remember that slope changes depending on where you are interpreting it. So right here, you can see why this slope looks like 0. The slope is basically 0. So that's why it looks like 0. And then as you keep going, now the slope looks a little bit steeper and a little bit steeper. And so do you remember that article you read called the centercept and how we talked about centering variables? If we were to recenter this so that this became 0 right here, what do you think about this coefficient? What would happen to it? Would it change or would it stay the same? I have one vote for it would change. What do you think at home? Do you think if we move this, now this becomes 0, which one's this, like 3, 4, is now 0.
It will become steeper.
It would become more, is that what you said?
Steeper.
It would be steeper, right, this and no longer negative. That's right, Adriana, so you'd have a positive coefficient here. But do you remember this from interactions and recentering? What about this one? Would it stay the same or would it change? It would stay the same. Because the amount that the slope changes as you move across values of x is still the same no matter where you go. It's always changing this much. So as you move things around, this term stays the same, but this one will switch around. Will move depending on where you are. Which is why you have to interpret them together as a whole. Now, before I move on to Colby's question about the gender variable, can I clarify any other things about statistical significance and interpretation of this linear and nonlinear slope?
Yes, could you repeat again?
You go next. Yes, repeat which again?
You said the non-linear one?
Say it again.
The linear and the non-linear one?
The interpretations of these two slopes?
Yes.
Sure. So let's do it one more time, which is that when I'm looking at these two slopes, I have to interpret them together. I can't interpret just one or the other necessarily when I'm thinking about conceptually whether these things are related to my outcome. What I'm saying here is that the slope of the line when pre-roulette is 0 is negative 0.388, which is not significantly different from 0. So I'm thinking about it at a particular point. But this coefficient here tells me that there is a relation between this size variable, relative size variable, and my outcome of math. It's just that it's not a linear function, it's a nonlinear function. It's a curved function. And I definitely just said that in a slightly different way than I did the previous time, but that's actually kind of my goal.
But
Go ahead, what was that?
I said got it.
I thought you said, what? So I was like, what? Okay. So now, the question that Colby brought up was, here with gender, gender is a non-significant predictor. Do I still need to worry about it? Do I still need to keep it in the model and think about it? And the answer is yes. You still should keep it in the model and still think about it. But in terms of sort of a model building question, that's a slightly larger question that we might get into toward the end of the semester. But generally, once you fit a model, you really can't interpret the model without considering all of the variables that are in it. We actually could get a very different result if we don't control for gender. Even though gender is not a predictor, a significant predictor in this model, we still could see a different effect of our other variables without it in the model. Okay, how does that feel? Any muddy points there that I can clarify for you?
Sarah and I were talking about how you would tell if it's concave or convex. We kind of figured out, like, it could potentially relate to the positive and negatives of the two data values, but then that's really only if it's like a perfect relationship. Is it just you interpreting the data and just what makes sense?
How would you tell if it's a concave or a convex curve? That's the question. So
So what we were initially saying was just like, okay, cool, with at least at the 0 point with like that negative and positive, we know that it's gonna start like that. And then once we get to a certain point, we can see that they're both positive now, so then it brings us to that kind of one. Is that like the only kind of thinking we can follow?
that's the only kind of thinking you can follow. Yes, exactly. Is to follow it through to sort of think about where would this go? If you have, well, there's actually rule of thumb, which is if they're both negative, then it's going to look like that. If they're both positive, did you draw it?
Yeah, very poorly, but yes, this is what we were.
The question is, how do you tell? Can I show the room? Oh, yeah. Yep, you got it. This is so cool. What is this thing? If they're both negative, it's going to go zoop, because your negative gets more negative. If they're both positive, it'll do that because your positive gets more positive. With a positive and a negative, then you end up with these opposite situations. But it really kind of depends on,
It's only if like it's at the perfect 0, perfect, if you started at where the tangent line is 0, just over.
exactly, only if you start where the tangent line is 0, which I think I didn't say in front of the mic, sorry, which only if you start where the tangent line is 0. It is also possible that you could catch a parabola like that, right? This is the Yerkes-Dodson curve. I'm not motivated at all. I become very motivated, and then I become less motivated again. In which case, that would be positive. I think it would have to be, I don't know what it would be. It could be any of the above, depending on where 0 is. You got it. Now I just can't find my... Okay, other muddy points on this before we do some other things. Okay. I actually don't have very much more. I just want to go over again what a nonlinear research question sounds like in case you decide you want to try a nonlinear model in the homework assignment for homework 6. So thinking about it here, the nonlinear term is testing whether the relation between x and y is a linear one or a not linear one. And you do it just like multiple regression and interactions. You always want to have a reason to test for that, not just, oh, maybe it's there. And just like with interactions, remember we talked about interactions as like freeing up the restriction that it was the same for everybody? This is like freeing up the restriction that the line is straight. So we're testing, can we give up that degree of freedom to test, to allow that relation to be less straight or not? And so the significance test is asking whether the null hypothesis is true, that the relation is not linear. So here's the next assignment that I have for you. This is the next activity I have for you today, which is I want you to think about the data set that you're using for this class. It could be the data you brought with you, or it could be the data that you're using that belongs to me, whichever one you're using. I want you to think about it, and then look at these 3 or 4. We've talked about a couple of different ways that an equation could look. And I want you to think about a question involving your data that involves a nonlinear relationship. And I'm going to give you about 5 minutes to think about a question right now that you think could make sense for your relations. Just like my idea of more beer is bad, but some beer is good. So if you want to think about it that way, you could think about like some stress is good, too much stress is bad. So try to use that phrasing to come up with an idea of how you will, what you could test. So take about 5 or 6 minutes to do that, and then I'm going to call on a random set of you to share.
First years and seniors to perhaps not.
Okay. So let me just jot that down. I expect the middle years will
I guess it's semesters, because I'm measuring in semesters.
it's not that they will have a lot of effort. Remember, we're thinking about the relation between effort and the outcome.
Yes, and so they'll have essentially a higher final grade.
So the amount of experience in semesters affect the engagement or effort in an asynchronous online course. So this one's context.
Yep.
So with a little bit of experience,
A little bit of experience, low semesters, we expect perhaps a lower final grade.
okay, but with a lot of experience,
Which is a lot of semesters, also perhaps a lower final grade.
cough, senioritis. Is that what you said?
Yep.
Okay, and then with medium experience,
We expect a higher final grade.
interesting. So I can imagine what that looks like. Do you want to draw it in the air for me?
I just did a wall.
Uh-huh, like zoop, like that. Let's see if I can, I don't have either one of those here, so go away. Like that. Nope, that's it. Go away. Oh my God. Stop. Stop it. Oh my God.
Oh,
Oh, now we can see it.
Not that.
I don't think my data's gonna do that.
That would be extremely impressive if your data would do that. There's probably some models you can fit that would do that for you.
Oh, no.
Okay, so there's an example of the idea of what that will look like. Get bigger. I know you can't really see it, so I'm going to try to, like that. Stronger relationship here. The only thing is that this then suggests that there is a negative association, right? Is that true? Between like your first semester of your junior year and your second semester of your senior year. You've got
I
to,
would suspect if they're taking courses not intended for them as an audience, that's the whole thing.
oh, interesting.
This course is intended for first and second year, so a few semesters. And so if you have like all your semesters under your belt and it's your very last one,
Then
it's
who
not
cares?
the most important course that you're taking.
Yeah, so it won't really matter as much.
Yeah.
Oh, interesting.
For financial aid, and you don't need the credits. You don't need to graduate.
So is this a question that you would be able to test in your data that you have right now?
You should be able to.
That's very interesting. Well, consider whether you would like to do that or an interaction, because now I kind of want to know. Okay, I'm going to roll another random die. One is on the computer. Okay, folks at home, I'm coming for you. I just have to find you. 1, 2, 3. That's Sarah. Sarah, can you give us your research question that you came up with?
I asked them, does the degree of social distancing increase with years of education, or does that relationship change with more years of education?
Did I get that right, Sarah? I'm laughing because I asked you twice on mute.
Yes.
So what do you think that relation is going to look like?
I think it will be positive, the strong relation initially, but then the degree of social distancing will eventually plateau despite increasing years of education.
Do you have it drawn that you could show us, or can you un thing and draw it in the air? Turn on your camera.
I think it might look like a log graph.
So not like any of these, you think?
It looks like the one in the middle.
This one?
Mhm.
I'm going to pull it down here. So here I have years of education. And here I have degree of social distancing. How do you measure degree of social distancing? Like how far somebody is from somebody else?
It was a scale of different types of behavior that is related to social distancing, I believe.
That's right. I forgot. So Sarah's using a secondary data set that we found. So it's a little bit harder. It's not like a survey that you gave out. So it's a little harder for you to answer. Okay, so as more education goes up, at first there's a really strong association, but then eventually more education isn't doing anything. So that's like, by the time you have a college degree, additional degrees doesn't make you more likely to social distance. I buy it. I like it. Okay, I'm going to do one more. Dun, dun, dun. That's you, Jelly. Can I get you to tell us your question? I may have lost her. Okay. I'm gonna roll again. 1, 2, 3, 4, 5. That's you, Chris Ann. Can you give me a research question?
Not at the moment, actually.
Hoda, can I pass it to you then?
Yeah. So mine is, does explanation of the stress level of parents with kids with special needs change by support needed to receive training? So I think by receiving more training, the stress level is gonna decrease till
okay, at first, like a little bit of support,
Yes.
or training is helpful.
Yes. Decreases the stress.
Okay, and then more support or training is, how would you phrase that, do you think? More support or training,
Less stress. And then it's gonna, and then receiving more support is not gonna change, the stress is gonna, stay the same.
doesn't help anymore?
Yeah. But I don't think it's gonna increase it, so it's gonna, stay steady.
Yeah, that makes sense. Doesn't help decrease stress anymore. Okay, so which one, does one of these fit that?
Maybe the third one?
This one?
Yeah.
This looks like to me, it's helping a little bit, and then it's helping a lot. So it's kind of like this, but upside down. So because if it's decreasing stress, then it should go just like this, but the opposite. Cool. I'm gonna. Oh, I may not be able to do that. But the opposite. So we have, I'm gonna steal this one that I made for you. And I'm gonna put it down here. So we're gonna do helping a little bit, then it's not anymore. Come here. Hey, stop it. Kind of like that.
Isn't it the negative increase in stress?
Oh, decreasing. Ugh. Literally the reason why I didn't.
Just full circle. Less stress, all the stress.
All the stress. Like that. Eventually, we've decreased it far enough that it's not helping anymore. Depending on where this axis is, it could decrease it all the way down so there's no stress. Or it could decrease it down so that just no more is helpful. Okay, good job. Depending on where that axis goes. Okay, that's it. Does anyone else have one that they'd like to share? I really just wanted to get 3 examples, and I feel like we've got 3 very different examples, which is nice. If anyone else has one that they would like to share, I would love to hear it. Otherwise, the end.